Hello and welcome back. In this video, we are going to take a look at the signals that constitute sending and receiving of information via UART on the oscilloscope that you can see on your screen right here. So that is my workbench. Let me just zoom out so you see a bit of it. I want it to fill the whole screen. Yes, I think this is okay. So this is my oscilloscope, and I'm going to show you the setup I've done so that you can also do the same thing. So let's go to the desktop, and over here you can see the very UART USB converter that I am using. It's called DSD Tech SH blah blah blah. To be honest with you, it doesn't really matter which USB to UART converter you use. I'm just using the particular one that I am using. Like, that's what I'm showing, so that if you don't already have one and you want to purchase, for you to be able to have repeatable results just as I would, then maybe it makes sense to fetch one of the one that I have. Otherwise, any other USB to UART converter should work. Now I'm going to hopefully, yes, this is good. So the one I have has the ability, it gives you the ability to change the logic level that you are working with. And then it also exposes all the pins that you need. So on the bottom of it, there is a pin for VCC, ground, transmit, receive, request to send, clear to send. These are for hardware flow control, like I explained in the previous video. It also comes with this jumper, just in case you want to do an echo. So the jumper is basically connecting the receive and the transmit lines together. So what it means is that whatever you use your host computer to send is also going to be received by the host computer. If you want such a setup without wanting to write code, then you can do that. And over here, it also allows you to choose the logic level for which your microcontroller, or at which your microcontroller operate. So for some microcontrollers, like ST microcontrollers or controllers from Nordic Semiconductors, mostly they are 3.3 volts. And if you go to the very old Arduino MCUs, you get mostly 5-volt logic. So you want to be careful to choose the right logic level depending on the microcontroller you are using. In my case, I have set mine to 3.3 volts because I'm not even connecting to a microcontroller now. I just want to operate at 3.3 volt. So what are the connections that I have made? It's pretty simple. I have just connected the USB side to my computer. Maybe let's go to the workbench and I will try to see if I can show you that. I also want to keep this video very short, but let's see. So I'm going to touch the workbench camera. Should I do this? No, I wouldn't. But basically, there is this oscilloscope probes here. Okay, I'll try to see if I can move this. And let me see if the camera is going to lock in. Yes. So this is the very converter that I showed you, right? And I have just extended the pins for transmit, receive. I only need transmit in this case. And then I have also brought in my ground pin here, which I will connect to the ground of my scope. So let's go ahead and then do the connection. So I am hooking the ground to the ground of the converter, and then I'm hooking the transmit to the probe of my oscilloscope. I think this is quite easy to set up, so I don't have to disturb my setup on the workbench here. And if we go to the desktop, yes. So if we go to the desktop, like you can see here, I am still using the serial monitor program that comes with VS Code. You can use any of the serial monitor programs that I told you about yesterday, right? You can use PuTTY or you can install Realtime, but I like what comes in VS Code. So I have connected the USB side. So this side, I've connected the USB side to my host computer, and then I have connected the transfer pin here, okay, to the probe of my scope, and I have connected the ground pin to the ground of my scope. So basically all that the scope is going to sense is whatever happens on the transfer line. And what that means is that if I use this software, if I connect to my converter right now and I use the software to send anything, the signal is going to be transmitted on the TX pin. And that is what the scope's screen is going to show. So let's switch to the desktop and then try to connect to the converter. So in here, I can see my converter's name here, BG01EXCXFTDI. On Windows, it might be COM something, COM1, COM9, COM10, depending on how many such connectors you do have. But I'm on a Mac, so look for the right name or port number for your converter on your Windows machine, if you're on Windows. So I click this, and then I'm setting the baud rate to 9600. The reason this is important is, I mean, I can set it to anything, but if I change it, I have to also change the time settings on the scope. And once we go to the workbench camera, I will show you the settings for the time. But basically, I'm doing a baud rate of 9600, and that means the period of one signal is going to be, you know, frequency is equal to 1 over period, and period is also equal to 1 over frequency. So if I divide 1 by 9600, then I get around 104 microseconds. So if you go to the workbench camera, you see that I have set the oscilloscope's time to 100 microseconds so that I can capture it nicely. All right, so now I can click on start monitoring. And nothing is happening here, right? Because we are not receiving anything. This is only set up for transmission. Okay. One other thing I want you to take a look at is we are going to send characters. So I have gone ahead to look up a table that has all the ASCII codes for the ASCII characters on the keyboard and their binary equivalent. So for example, if I send capital A, I expect to see 10000010. If I send capital G, I expect to see 11100010, right? Now, we have this table here so that we can compare it to the signal that the oscilloscope is going to show. Now let's go to the workbench camera. This video is going to require me to make a lot of switching of scenes. I have two views actually. This one is going to show what I'm doing on the desktop and also the workbench, but I don't think the desktop is legible enough, but we will try. If it is disturbing, I will switch to a better view. Okay, so now we are connected here, and then you can also see my oscilloscope here. Now let me explain some of the settings that I have on the oscilloscope. Let me get maybe my Apple Pencil so I can use that to as a pointer on the screen to avoid touching things I don't want to touch. All right, so on my scope, I have set the vertical scale to 1 volt per square. Okay, so this one here is 1 volt, this is 1 volt, this is 1 volt. So you can see that between here to here, it is measuring 3 volts. And then this is a bit midway between 3.5. So that is 3.3 volts. And that is a confirmation of the fact that I have set my converter to be operating at 3.3 volt logic level. And if you look up here, it is showing 200 microseconds, but I can also adjust that time scale to go to 100 microseconds, and that is going to help me to capture some signals, but I want it to be close together. So let's go back to 200, and then I'm going to show you how I'm capturing. Okay, so to do that, well, let me start by, let's say I just run this. Okay, cool. You see, at this point, nothing is being transmitted. This is going to help you to understand how UART signals get transmitted. So the oscilloscope is hooked to the transfer pin of my converter, and you can see here that it is reading 3.3 volts. So when the line is idle, it is pulled up. Okay, it is pulled up. So when the transmit line isn't transmitting anything and you read the voltage on it, it is going to read 3.3 volt or whatever the logic level you have set for it is. Remember that I also mentioned that we have what is known as the start and stop signal. So for the transmission to begin, it will indicate a start bit. And the start bit is by bringing the transfer line low for 1 clock cycle. And that is what is going to trigger the receiver to begin to sample based on the agreed baud rate. You get it? This is just a practical of the very first video I did explaining the theory of UART converter or UART communication. All right, so how am I going to be able to capture when I transmit from my host computer through the UART, and then I want to see that on the scope. On my scope, I am doing edge detection. I know that when it starts transmission, and I show my hand again, I know that when it starts transmission, it's going to pull the transfer line low all the way to 0. So I'm setting a trigger so that the scope will start capturing samples when this line comes below a certain threshold. I'm not teaching about oscilloscopes here, so I don't want to go too much details into the specifics of my oscilloscope, but basically this whatever it is, this triangle is an indicator of the threshold I have set for it to trigger when the voltage drops below 8. Okay, and I guess that is it for now. So I'm going to go to a mode where now the oscilloscope is going to wait for it to be triggered, then it will capture the signals, right? Now let's go to the desktop and let's check something. Let's say I'm going to transmit the character capital A. We expect to see 10000010, and this is the least significant bit, and this is the most significant bit, right? So now let's go back to the workbench. I'll try to show both workbench and the desktop. If it's not working, like I said, I will switch. Okay, so maybe let me go to just the desktop for the first time. All right, so here I'm going to transmit the character capital A, and then I'm pressing enter. And so you can see that the terminal program said it has sent UTF encoded message A, right? Now let's go to the workbench and let's go and see what is happening on the scope. Now, on the scope, you can see that it was still in the idle state, showing 3.3 volts, and then it dropped down 1 clock cycle. Remember, my time scale is 200 microseconds, and so the period is 104. So one cycle is going to be 100 microseconds, right? Now look at it well. It was high here, and then it dropped, okay, and then now it went up again. So this is the start signal. It is signaling the recipient. In this case, it's the scope that is reading. But if there was another microcontroller or any setup on the receiving end, then it's going to trigger that setup to begin to sample the line for the data that is being transmitted. So the start bit is 0, and then it transmitted a 1 because it went up 1 clock cycle. So this is 1. And then I think this is 0, 0, 0, 0, about 4 zeros. It came back to 1. It goes down again. And then it goes back to the ideal state, because in between here and here, the information has been transmitted. 8 bit has been transmitted, including the stop bit. Now let's go to the desktop. I sent the character A, right? So let's go and check what is the ASCII binary for character A. And you can see that it is 1, and then followed by 1, 2, 3, 4, 5. 5 zeros, and then there is a 1, and there is a 0. Okay? Now let's go back to the desktop or the workbench, and then you can see the oscilloscope actually has a function that can help us to decode this. So let's do the decoding so that it's easier for us to see what's going on. So I'm going to press decode here, and you can't actually see my hand, but okay, now you can. So I'm setting it to decode the signal, and I'm saying it should display. So you can see that it is receiving 1 0 0 0 0 0 1 0. How do we check it with a signal? Like I said, it is idle. It comes down to signify that transmission is about to happen, and then immediately it begins transmitting. So this is 1, okay? It goes high, so this is 1. That represents this 1 here. So it looks like it transmits the least significant figures, the least significant bit first, okay? So this is 1, and then it goes down, it stays down, it stays down, it stays down about 5 times. So that is 0 0 0 0 0, and then there's 1 0. So it goes up, that is the 1, and then it goes down again to transmit the 0, and then it comes up. One of the high values here is a stop bit, depending on what we configure. Remember, in code we can configure 0.5 stop bit, 1 stop bit, 1.5, or 2.0 stop bit. So it indicates the stop, and this is supposed to help the receiver to know that all the bits in the data that it is interested in transmitting has been transmitted, and so it can stop sampling. Let's send another character, let's say G, right? So let's come to the desktop here. Let's see the character G. What is the character G in binary? It is 1 1 1 0 0 0 1 0, right? So put this in your head. I know you can write it somewhere so that you can compare it to what you will also see on the oscilloscope, right? So now I'm going to the serial monitor program, and I'm going to send the character G, as you can see here. And let me put the scope back in a mode where it is going to be listening. So this is G. I'm not pressing enter yet. I'll switch back to the scope. Maybe let's try this. I think it works. All right, so I'm here and I'm now going to hit enter in the serial monitor program. So I hit enter and boom, the oscilloscope captures the information. And it has already also decoded it for us. So you can see that to send the character G, it was high for the ideal state. It came down to 0 to indicate the start of a transmission. And what do we have here? It has to transmit 1, 1, 1. So high, high, high. So it stays high for 3 clock cycles. Okay? And then it has to come down to transmit 3 zeros. So 0, 0, 0. It stays down for 3 clock cycles. And then it has to transmit 1. So it goes up high for 1 clock cycle, and it has to transmit 0. So it comes down for 1 clock cycle, then it goes up to show whatever is the stop signal, stop bit, whether it is 1, 2. At this point, I don't control. It depends on what has been set in the serial monitor. But basically, it goes back up to 1 or logic level 1 to signal that it has finished the transmission. So the essence of this video is just for you to appreciate how some of these hardware peripherals work, and also make it possible for you to have a mental model of how to think about it when you are transmitting information. You can see that at the end of the day, it's just a stream of zeros and ones. And how the recipient interprets it determines whether the communication is going to be correct or not. For example, this is 0100. Oh, let me read backwards to be correct. 111000110, right? How do we know that this represents the character G? Because it could be anything, right? That is why there is encoding and there is also decoding. So for the communication to happen properly, the way it was encoded should match the way it is decoded. So for example, if the sender is sending ASCII characters, but the recipient reads these bits and tries to interpret it as an integer, then I might send a character and the recipient program might be seeing an integer. All right. So this is why whenever you take any sensor, and we'll work with something like that, whenever you take any sensor and the sensor says, I send my data over UART, it is not enough to just hook it up, connect it to the UART peripheral of your microcontroller, and then just start reading. You have to read the manual or the data sheet of the sensor to understand how to interpret the bits that you will receive over the UART peripheral. I believe this example has been able to help you have a better understanding of how the UART protocol works, and I believe it's also going to help you to have a better imagination of what happens over the wire when you are sending information over UART. Thank you very much for watching this, and I will see you in the next video.